customer webinar. We have audience from Latin America, and I also have people from Canada. So this presentation will be conducted in English. However, for the people in Latin America, feel free to put your question in Spanish if you need to. I'm going to be pending to the question in the chat. However, the question will be taken at the end of this presentation. So we appreciate if you can write them as soon as you come to your mind. Also, I want to make sure and let you know all that we're going to be recording this webinar for technical support and future reference. So with that being said, I'm going to introduce our presenter today, Mr. Craig Young. He's our HPLC product manager and have been with us for more than 5 years now. He has plenty of experience with the prominent series and all the technique from Shimatsu HPLC. So with that being said, I'm going to introduce Mr. Craig Young. Thank you.
All right, Sam, thank you so much. So thanks everybody for tuning in with us today. I really appreciate your attention. My goal is to introduce you to an exciting product from Shimadzu, the Shimadzu Prominence IC, which is an anion specific ion chromatograph suitable for wide-ranging applications, including environmental, medicinal, and food science. As Sam said, I'm the HPLC product manager, and I have a very large product line to manage. And I'm exceedingly excited about our new Prominence ion chromatograph. As I'm sure you will agree once you hear what I have to say about it, it's an exciting addition to our marketplace. So I want to tell a bit of a story of IC as we go along, and I'm an educator first and foremost, and so I like seeing the light bulb come on for people as I'm helping to promote my product. I like to educate people in the process. So let's get started with just a topical introduction and take a look at the different topics to be presented in today's talk. First, what is ion chromatography? We're going to look at an introduction to ion exchange and IC systems. We're going to look at where IC is used very briefly, talk about conductivity detection. Then we'll look at HPLC versus single column IC versus suppressed IC, different terminologies. What is suppressed IC and why does it matter? What is suppression all about, how it works, and why it's necessary. We'll look at different suppression technologies on the market, look at detectors briefly, and then even resins for IC columns. Then we're going to introduce the nuts and bolts of the Shimadzu Prominence IC, look at the flow path a little bit. We'll look at column recommendations from Shimadzu and then best practices with our new suppressor. If you happen to become a partner with us in ion chromatography. And then briefly, we'll look at some applications at the end. Please keep in mind your questions for the end of my talk. As Sam suggested earlier, that allows me to go smoothly through the story that I want to tell. And then we're certainly happy to try to tackle any questions you have there at the end. What is ion chromatography? Shimadzu is first and foremost a chromatography company. High performance liquid chromatography, which is my product line, is the mainstay of what Shimadzu does. But we use a different terminology when talking about ion chromatography. The terms are different, but the principles are the same. We have some additional concepts in ion chromatography to tease out. Over the years, liquid chromatography has become the most impactful analytical technique to separate, identify, and quantify analytes and mixtures. Let's think about HPLC. HPLC is a liquid chromatographic technique used primarily for the analysis of organic constituents in mixtures. The separation occurs through the interaction of the analytes, organic molecules, with a mobile phase, typically a collection of organic solvents of various chemistries, and a stationary phase, usually silica-based particles with a bonded surface chemistry packed into a column. The separation or retention mechanism is typically some combination of hydrophobic interaction and dipole-dipole interactions. Ion chromatography is used primarily for the analysis of inorganic ions. In IC, the stationary phase is an ion exchange resin, and the mobile phase, usually called an eluent, is an aqueous pH-adjusted buffer system. Separation occurs through the exchange equilibria between ions in solution and ions of like sign on the surface of the resin. Where is ion chromatography used? The lion's share of IC systems and applications are in the environmental sector. In particular, the analysis of drinking water, which is the main application of IC, and it is an industry regulated by the US Environmental Protection Agency. EPA methods 300, 300.1, 314.1, 302, 332, 314.2, and 557 all have to do with the analysis of water-soluble ions at regulated levels. Sometimes the ions are naturally occurring. Other times they're byproducts of disinfectants used in water treatment. Other relevant markets might be power industry, semiconductor industry, food and beverage, and even pharma. The most common analyte types of concern in IC are the anions present in drinking water. For example, sodium chloride in water dissociates into sodium ions and chloride ions. The common negative ions are called anions, which are fluoride, chloride, nitrite, nitrate, bromide, sulfate, and phosphate. Common positive ions called cations are sodium, potassium, ammonium, magnesium, and calcium. The detector of choice for these ions is the conductivity detector. Two gold electrodes, an anode and a cathode, are in the flow cell, and a constant voltage is applied between them. When ions move through the cell, they cause a change in the current flowing between the electrodes, hence detection. Let's look at some interesting little notes about conductivity detection in general. It is the most common detector with IC systems and the detector of choice for the environmental market applications. That is drinking water analysis with EPA method 300.1. The response factor in a conductivity detector is analyte dependent. Units are reported in microsiemens per centimeter, a measure of electrical current. Interestingly, pure water has a response factor of 0.05 microsiemens per centimeter. This corresponds to a resistivity of 18 megohm centimeters. Those of you who generate ultra pure water using a millipore or similar type of filtration apparatus would recognize the 18 megohm. That's typically what we're looking for to indicate purity. The interesting thing is that that yields a response factor for pure water of 0.05 microsiemens per centimeter, which is a good touch point of reference when doing IC. The conductivity detector is very susceptible to temperature variation. A change in 1 degree centigrade in solution temperature can cause a change of roughly 2% in electrical conductivity. Various methods of avoiding temperature variations have been devised, such as constant temperature cells. Point of note, the Shimadzu CDD10AVP conductivity detector, which we're going to present as part of our IC system, features a thermostatically controlled flow cell installed inside the column oven for an extra measure of temperature control. This produces a more stable baseline and more reliable peak integration for quantitation, which benefits in high sensitivity analyses. It's useful to distinguish IC from HPLC, which we know and love. I know and love it because it's my product line. Using a schematic of the flow path for comparison. The main differences between HPLC and IC are as follows. In HPLC, a pump produces a flow of solvents, methanol, acetonitrile, water, etc., into an injector, which is connected to the inlet of a separation column. The column is typically packed with tiny silica-based particles with a modified surface chemistry. The outlet of the column is connected to the flow cell of the detector, commonly a light-absorbing detector like UV or diode array. It could even be perhaps a mass spectrometer. Under flow, the analysis sample is injected onto the column. Differential migration occurs, producing separated analytes which flow individually to the detector, where response occurs, producing a peak for each analyte. The separation column is typically housed in an oven for the sake of temperature stability. We're not looking to achieve a magical separation quality with temperature. We're really just looking for the stability, the reliability of the temperature so that we get repeatability. The name of the game is repeatability, that you can do the same run 5 times in a row and it looks like one chromatography run. In ion chromatography, a pump produces a flow of eluent, which is aqueous buffer salts, into an injector, which is connected to the inlet of the separation column. The column is typically packed with an ion exchange resin that's polymeric in nature. The outlet of the column is connected to the flow cell of the detector, commonly a conductivity detector. Under flow, the analysis sample is injected onto the column. Differential migration occurs, producing separated analytes which flow individually to the detector where response occurs. This produces a peak response for each analyte. Temperature stability in IC is critical, and both the separation column and the conductivity detector flow cell in Shimadzu's system are housed inside the column oven for an extra assurance of thermal stability. IC is sometimes called single column IC. More on that in a few minutes as we talk about this juxtaposition of HPLC and IC. Hopefully this makes sense to you. IC, also known as single column IC, has a limitation of sensitivity. This is solved using a suppressor. Suppressed IC has one very important difference from single column IC. That is, a suppressor device is inserted between the ion exchange column and the detector. The suppressor pictured here in this schematic is an electrolytic suppressor. What is suppressed IC and why does it matter? In IC, the eluent buffer salts are conductive and produce a high signal response. The conductivity detector is a bulk property detector which makes a difference measurement between the analytes and the eluent background. The goal is to maximize the response from analytes and reduce the response of the eluent background. That is, we want to maximize the signal to noise of the analytes. So let's look at a little bit of the chemistry involved. If potassium hydroxide were the eluent modifier of choice, potassium hydroxide in water is in equilibrium with potassium ions and hydroxide ions, both highly conductive to a conductivity detector. If carbonate bicarbonate buffer systems are used, sodium carbonate in water is dissociated in equilibrium terms into sodium ions and carbonate ions, which is further in equilibrium with carbonic acid and hydroxide ions. The equilibrium is constantly shifting using Le Chatelier's principle. Again, the CDD detector, Shimadzu's terminology, is making a difference measurement between analytes, the ions in dissociation, and the bulk property of water. So we're trying to maximize the signal to noise ratio. The suppressor inserted between the column and the flow cell of the detector saves the day for sensitivity. A suppressor is a device that uses chemical processes to change the chemistry of the eluent to a less conductive state, increasing the signal to noise of the analytes. These chemical processes deplete the suppressor and it must be regenerated. So let's look a little more deeply at how suppressed conductivity IC works. Here's an application example from US EPA method 300.1 for drinking water anions. The column chemistry that we're illustrating is a quaternary ammonium salt. The detector is conductivity. The eluent is sodium carbonate. Part A of method 300.1 for US EPA is for the analysis of bromide, nitrite, chloride, orthophosphate, fluoride, and sulfate. Part B is the inorganic disinfection byproducts, bromate, chlorite, bromide, and chlorate. The method detection limit is in a range from 1 to 20 micrograms per liter. That's parts per billion. So what we're looking at on the screen is a typical chromatogram for the baseline separation of the common drinking water anions. In non-suppressed ion chromatography, the detection limits may be very low, not suitable for EPA method 300.1. Enter the suppressor. The bulk property conductivity of sodium carbonate solution is inherently high. A suppressor may be inserted between the column and the detector to reduce that background signal. With suppression, 3 orders of magnitude lower detection limits are achieved. Suppression chemically alters the mobile phase. So what you will notice in this idealized chromatogram display is that sodium carbonate reveals a rather high baseline due to its inherent high conductivity. The suppressor chemically alters that eluent to reduce the inherent bulk property conductivity dramatically, as in 3 orders of magnitude, to deliver a new lower bulk property baseline. This has the effect of causing a greatly increased signal to noise for the analytes in question. For carbonate bicarbonate systems, background suppression converts most of the carbonate to water, reducing the background conductivity. Removal of sodium ions across the membrane also helps to drive the equilibrium to the right. Notice the equilibrium that I'm illustrating at the top of the screen. Sodium carbonate in water is in equilibrium with sodium ions and carbonic acid, which is also in equilibrium with CO2 gas and water. So in practice, practically speaking, a suppressor will generate, as a byproduct of this chemical alteration, carbon dioxide gas. Bubbles will form and they leave the system. At the same time, the effective conductivity of the analytes is enhanced because the ion exchange mechanism results in a more highly conductive form for the analyte ions. In my illustration at the top of the screen, sodium fluoride in water forms dissociated sodium ions and fluoride ions, which are in equilibrium with sodium ions and hydrogen fluoride, a more highly conductive form. So this is a further enhancement of the signal to noise for the analytes. Next, let's look at the water dip. The water dip, by definition, let's back up. remember that our ionic analytes are all water soluble. The injection matrix is mostly water. So water emerges from our chromatography column unretained. The detector response takes a dive. Why? Because of water's inherent much lower conductivity value. And what did we learn earlier? That conductivity value ideally is 0.05 microsiemens per centimeter. So the lowest point of the water dip indicates the conductivity for pure water. The time position of the water dip indicates the cumulative volume of the suppressor and the column void for the anion column. There are two types of suppressors used in ion chromatography: chemically regenerated and electrolytically regenerated. We call these chemical suppressors and electrolytic suppressors. There are advantages and disadvantages to both. All suppressors are consumable items and will be depleted over time. Remember the statement earlier, a suppressor chemically alters the eluent in ion chromatography. In the process of doing so, it becomes depleted and it must be regenerated. But they will also become contaminated over time due to dirty samples. Dirty matrices like dissolved metals and intractable organic materials. Cleaning procedures exist, but ultimately a suppressor must be replaced at some point, depending on the cleanliness of the eluent and the samples. I can't stress this enough. All of the major manufacturers of ion chromatography systems that offer suppression would make the note to you that a suppressor is a consumable item, and the frequency over which you have to replace it depends on the cleanliness of your samples and your eluent. Let's briefly look at detectors for ion chromatography. Conductivity detector, as stated earlier, is the only detector type considered here in detail, as it is the most common and applicable for the environmental market. However, you should always consider the possibility of adding a UV detector to an IC for analytes that possess a UV chromophore. These might include organic acids, bromide, iodide, nitrate, nitrite, thiosulfate, and cyanometal complexes. In addition, IC systems can be hyphenated as a front end or an inlet chromatography mechanism for a mass spectrometer. With MS detection, due to its specificity and sensitivity, it may be also used coupled with IC. An example is the quantitative determination of perchlorate in drinking water at low parts per billion levels. Another type of detector on the market is pulse damperometry. This is an alternative for electroactive species such as water-soluble carbohydrates, sugar alcohols, amino acids, and organic sulfur species, to name a few. In pulse damperometric detection, the electrical potential is cycled several times per second. The USP methods exist for measuring galactosamine and glucosamine at low levels in biological samples. PAD is an extremely sensitive technique. A word about resins for IC columns. Anion exchange. The stationary phase resin is positively charged quaternary ammonium bonded cation groups, and negatively charged analytes are attracted to it. It is the most common resin used for the analysis of inorganic anions. The pH and ionic strength of the eluent plays a large role in the separation of the analytes on such a column. Strongly retained anions will elute later in the chromatography. Doubly charged anions will retain longer than singly charged anions, etc. Cation exchange. The stationary phase resin is negatively charged, as in sulfonic acid bonded anion groups. and positively charged analytes are attracted to it. Strongly retained cations will elute later in the chromatography. Doubly charged cations retain even longer. The eluents used for cation chromatography are very different from anion chromatography. Now let's look at the nuts and bolts of the Shimadzu Prominence IC. With the Shimadzu Prominence IC, you can determine anions with the high performance and ruggedness you would expect from the most trusted name in LC, Shimadzu. Built-in electrolytic suppressor with a ruggedness to set a new industry standard. Sensitivity for the EPA drinking water methods. High-speed autosampler delivering fast, clean injections with minimal carryover. Shimadzu is famous for this. A small system width, that is a minimum of bench space taken up by the IC, but a maximum in bench space efficiency. And then finally, dependable and reproducible eluent delivery with minimal baseline pulsation. With the Prominence IC, we're featuring an inert flow path. Why? Because it gives you peace of mind. All wetted surfaces of the IC are inert to the eluent and sample matrix, so there's no worry about leaching or corrosion. The flow path is compatible with corrosive eluents like potassium hydroxide, important for some IC applications. The suppressor's lifetime under high pH conditions is maximized because the flow path does not contribute dissolved metal ions. And then finally, the ion exchange column's lifetime is maximized because the flow path does not produce column clogging particulates. Another word about small footprint. The Prominence IC occupies only 16.5 inches of bench space, maximizing your bench efficiency. I was very taken with the size of our IC. It's truly remarkable. In today's climate, where horizontal bench space is expensive, vertical space is typically cheap. Let's look at the components that comprise the IC. The conductivity detector, the CDD10AVP. This provides sensitive yet stable detection resulting from two layers of thermal regulation. The temperature-controlled flow cell is mounted, as I said, inside the column oven. The ICDS-40A anion suppressor. This is a low noise and minimized internal volume suppressor for efficient baseline suppression with the highest chromatography quality. Next up is the LC20AI salt eluent delivery pump, made of inert materials with low pulsation eluent flow for uncompromised IC. The CTO40S column oven. This is a forced air heating column oven in a narrow profile, providing heat capacity up to 85 degrees centigrade. And then finally, the auto sampler, the SIL20AC inert version, for high-speed injections from 0.1 to 2,000 microliters with the lowest of carryover. So let's look at the new Shimadzu anion suppressor, the ICDS-40A. The term electrolytic suppressor is common in the industry, referring to the electrolysis of water used in regeneration. Shimadzu's ICDS-40A anion suppressor is called electrodialytic. This is a term coined by Shimadzu because it uses a unique folded flow path with a patent pending design for double efficiency. The increased membrane surface area for highest efficiency of both background suppression and electrolysis regeneration. It features minimized internal volume, which minimizes peak broadening. And in use, it's practically set and forget. Literally, on our conductivity detector, you set a current value to apply to the suppressor, which we set for you when we install the system. It's set and you forget it. You periodically keep your eye on the voltage being reported by your suppressor. Over time, if you have been injecting dirty samples, what you would notice is that over a period of months, perhaps, the voltage will begin to increase from a nominal starting value of perhaps 5 volts. And that at some point, the voltage would indicate that your suppressor is becoming fouled. So you have some kind of an indicator when you need to replace that consumable item. Not to imply that it happens quickly, but again, it is a consumable item that will have to be replaced depending eventually on the cleanliness of your samples. The small internal volume of the ICDS-40A results in a maximum quantitative performance. The water dip is narrower and post-column peak broadening is minimized. The separation of fluoride from the water dip, which is critical in drinking water analysis, is improved for low-level quantitation. With inferior IC columns and large suppressor volumes, the band broadening can be significant. At low analyte levels, as in single-digit parts per billion, the water dip can be so large that the fluoride peak sits on the upslope of the water dip, making peak integration less accurate and less repeatable. The more we can retain the fluoride away from the narrow water dip, and the narrower we can keep that water dip, the better the outcome quantitatively. The name of the game in chromatography, as I said to start my talk, is first and foremost repeatability, whether it be in HPLC or IC. The ability to get the same quantitative results is paramount to high confidence in quantitative results. The ability to get repeatable suppressed anion IC results over thousands of injections coming from a pump that produces consistent flow, an autosampler that delivers consistent injections, a rugged and efficient suppressor, and a detector that is stable in its response over long periods of time. So what we're looking at is some actual testing results on the Prominence IC system, over 1,000 injections, and you'll notice excellent repeatable results over that test period. Next, let's look at a little bit about autosampler performance. The SOL-20AC inert autosampler features a direct inject, that is needle in flow path design, which keeps carryover to a minimum. Shimadzu invented needle in flow path, and so we have always been proud to offer autosamplers that are the cleanest, fastest instruments around, delivering the lowest in carryover, offering multiple different cleaning options for needle rinse, and offering excellent specifications for linearity. The fast clean autosampler delivers the precision necessary for a correlation coefficient routinely of better than R squared 0.999. With our Prominence IC system, we offer Lab Solutions chromatography data system. Lab Solutions is offered as a standalone software solution or in database and client server versions. The advantage being that Lab Solutions is the ultimate in data integrity. Lab Solutions provides a software solution for the storage of data from all of your Shimadzu instruments, from FTIR, UV-Vis through the chromatography instruments of GC, IC, and HPLC. Feature-rich yet easy to learn. And that's easy for me to say because I do this for a living and I know my software. But we find that Lab Solutions is quite easy to learn, quite easy to teach to other people, and a rock-solid performer. Now let's look at some best practices in IC, and I've divided this into general comments and then comments specific to the Shimadzu anion suppressor. First, the general comments. More than 80% of all issues in ion chromatography are because of poor water quality. Use only the highest quality water for the eluent, 18 megohm or greater resistivity. Second, dirty sample matrices will reduce the performance of the system over time. Suppressors may become contaminated, columns may become clogged. Always filter your samples using polyether sulfone syringe filters prior to injection. We've done testing and have determined to our satisfaction that polyether sulfone is the most effective filter with a porosity suitable for particulate removal, and yet doing so without with minimal leachables into the matrix of the sample. For recommendations for the Shimadzu anion suppressor, use carbonate bicarbonate eluent for anion determinations only. During suppressed anion analysis, avoid organic solvents as eluents or modifiers, as the anion exchange membrane of the suppressor could be damaged. The suppressor is set to operate at a constant current of 180 milliamps. At that value, a new suppressor will show a voltage of perhaps 5.5 volts. Over a long period of time, a rise in suppressor voltage can indicate contamination. The ICDS-40A power supply will automatically turn off if the voltage exceeds 18 volts to protect the suppressor. Next, let's just mention some IC columns in general. These are our strongest column recommendations with our system, but note that with the Prominence IC, you can use any IC column from any manufacturer. We routinely use Shimpack columns from Shimadzu and Shodex columns as well. And I'll show you some chromatography examples shortly. For anions, the Shodex SI94E, that's a 250 by 4 millimeter, 9 micron polymeric bead. The Shimpack, the Shimadzu Shimpack IC SA2, also in a 250 by 4 millimeter, 9 micron bead, are good performers for general anion analysis. For cations, the Shodex YS50 in a 125 by 4.6, 5 micron material, or the Shimadzu Shimpack IC SC1 in a 150 by 4.6, 6 micron material. Give excellent results. This is a chart simply comparing anion columns that we offer and cation columns that we offer by part number, and then the target ions for each of the column types. Quality chromatography for the 7 common anions in a reasonable time frame of 15 minutes is the focus of this next slide. This is the EPA method 300.1. Note that 50 or even 100 microliter injection volumes are common in IC because the concentration of target ions is quite low, maybe in the low microgram per milliliter range or parts per billion. Quality chromatography for the 7 common anions and the disinfection byproducts in one run. This is for EPA method 300.1 parts A and B in under 27 minutes. Note the excellent baseline resolution and peak symmetry. I'm very happy with this chromatography. Let's look at quality marks. This is general recommendations of what to look for in your IC chromatography. These are the hallmarks of good ion exchange columns and performance for the system. Peak symmetry and retention of the fluoride peak away from the water dip. These are high marks for both qualities, which result in the ability to quantitate at low levels for the analytes, particularly fluoride, at low levels repeatedly. With inferior IC columns and larger volume suppressors, the band broadening can be significant. At low analyte levels, that is single-digit parts per billion, the water dip can be so large that it interferes with the quantitation of the fluoride peak. Once again, as I mentioned earlier, the more we can retain fluoride away from a narrow water dip, the better our quantitative outcome. Just briefly, I wanted to show you some cation determinations using the Shodex IC column YS50. And really, I want to point out the difference in mobile phases. Instead of carbonate bicarbonate mobile phases that we would see in the anion separations, here we're using mobile phases or eluents that are 4 millimolar methane sulfonic acid, or buffer systems comprised of tartaric acid and dipolinic acid and boric acid. Very different approach. We don't necessarily recommend a suppressor for cation determinations as well. So you could bypass the suppressor entirely if you're doing cation determinations with the Shimadzu prominence IC. More interesting mobile phase combinations for cation determinations. Briefly, I just wanted to mention some supporting applications and notes that we can provide as you request them. Even though these are labeled HPLC, it's because that's my product line. HPLC application note number 21 is in support of anion determinations. That's the determination of EPA method 300 anions using the Shimadzu IC system. Number 22 is the determination of 10 anions for EPA method 300.1. HPLC number 24 is the rapid analysis of 7 common anions in water using suppressed conductivity IC. And then finally, the determination of organic acids using suppressed conductivity ion chromatography. This is an interesting application that we have finished the application note a few months ago. Perchlorate naturally forms in the atmosphere, especially in the arid states of the southwestern US. It also occurs from the manufacture of a wide variety of industrial compounds. For instance, it's used as an oxidizer in the manufacture of munitions and fireworks. Perchlorate is considered toxic in that it may cause dysfunction of the thyroid gland and may lead to reduction of thyroid hormones. The EPA has established a lifetime drinking water health advisory of 15 part per billion for perchlorate to reduce health risk. More than 10 states of the United States have established health advisory levels for perchlorate in drinking water ranging from 1 to 18 ppb. For example, California and Maryland have proposed such standards as 6 ppb and 1 ppb respectively. A few quantitative methods for perchlorate have been developed by the EPA. Method 332.0 is one of the most sensitive, using suppressed anion chromatography coupled with mass spec. And that's the heart of this application note, is the Shimadzu prominence IC system coupled with our LCMS 2020 mass spectrometer for excellent results down to 1 ppb level. Finally, I just want to point out again a re-emphasis really of our main environmental applications for the Shimadzu prominence IC. And the first is EPA method 300. The next is EPA method 300.1. That's the 7 common anions for drinking water. And then those plus the disinfection byproducts, also for drinking water. Not just drinking water, but surface water, mixed domestic and industrial wastewater, groundwater, reagent water, and then leachates also. A new upcoming industry is actually water reclamation. That is the ability to reclaim water from industrial sites by cleanup procedures. So the ability to confidently quantitate the anions present in those water supplies is of great importance as well. So thank you so much for your attention. That's all I want to talk about with the Shimadzu Prominence IC. I hope it answers a lot of questions for you. And what's your appetite for more? And I'll turn it over to Sam, who's going to help me look at any questions that have come up.
Thank you very much for that presentation, Craig. It's an excellent information, excellent product. If anybody have any question, have 2 choices here. You can put it on the chat, or you can open your microphone and talk directly if you're comfortable to talk in English. You can talk directly to Mr. Craig. If not, you can put it on the chat, put it in Spanish, la pueden poner en español para las personas de Latinoamérica. ¿Alguna pregunta? Any questions? Okay. Mr. Nat Britzing is asking, what is the IC column made of?
The IC column?
Mm-hmm.
Typically, the IC column is chosen in a chemistry suitable to separate the analytes of interest. So let's go back to the graphic that I showed earlier. And just to support what I'm about to say. Let's see. Yeah. Typically in anion exchange, which is anion IC, which is the heart of the talk today, the stationary phase resin is positively charged, and the typical bonded phase is quaternary ammonium cation group. So typically it's a PSDVB polysulfone divinyl benzene material whose surface is modified with quaternary ammonium chemistry. That's the most common stationary phase for IC among the various manufacturers, by the way.
Okay. Thank you, Craig. I have another question here from la señorita Pamela Muñoz. She's asking, what is the ideal syringe filter for pore size or ion chromatography sample preparation?
Yes, I would give the same answer for an HPLC question. I believe the ideal porosity for syringe filters is 0.45 micron membrane materials. And 0.2 is even better, but 0.45 is a little more forgiving, and yet it's small enough porosity that it catches all of the particles we need to worry about.
Thank you. So basically like a HPLC.
Very much, very much.
Okay. Any other questions from the group? And looking at the chat, I don't see any other question. Remember, you can also open your microphone. I have a question here, una pregunta del señor Jorge Juventino Avenda. He's asking, the best way to regenerate is using the suppressor?
The suppressor, if you recall, comes in 2 flavors in the industry. Shimadzu's flavor of suppressor, the ICDS-40A, is a electrolytic suppressor. It's regenerated from the electrolysis of water electronically. The other flavor that is on the market from some companies is a chemically regenerated suppression technique. They're both valid. both chemically regenerated and electrolytically regenerated are valid suppressors. A chemically regenerated suppressor is highly sensitive. It allows you to do fantastic sensitive anion chromatography. The downside to the technique is that you have to manipulate caustic acid solutions in order to regenerate it. So it literally uses a concentrated sulfuric acid solution to regenerate the suppressor. One type that's on the market uses one chemically regenerated IC suppressor cartridge while you're regenerating another one. And then you move a turret, they're mounted onto a mechanism, and you move one into place for active analysis while the other one is being regenerated. Does that make sense to you?
Yes.
So both types are valid, both are commonly used, but I'd say the convenience of electrolytically regenerated suppression far outweighs any disadvantage it might have as far as sensitivity. Very few people do the kind of sensitivity work necessary that they would need chemically regenerated suppressors.
Right, and I require maintenance, right?
Much higher maintenance required in a chemically regenerated suppressor. Not to criticize anything on the market, they all work. They're all very successful with different approaches. And I would say the advantage of electrolytic regeneration is the set and forget nature of it. You simply set a current in the instrument, and then you just watch it over time. It will simply work. Mm-hmm. And then there are cleaning procedures that can work, but it's regenerating itself without you having to worry about it, which is a great advantage.
Perfect. So is there any other question here in the chat? Sue, she's asking, what is the typical sample size?
Typical sample size is between 50 and 100 microliters injection. Now, you may recall in my talk that the Shimadzu IC is capable of injecting as little as 0.1 microliters and as much as 2,000 microliters, that is 2 milliliter injections. You typically will inject between 50 and 100 microliters, noting that drinking water typically has a low level of anion content. Concentration is quite low. I'd say the most common injection volume is 100 microliters.
100 microliters. Thank you. And I have another question here from la señorita Pamela Muñoz. Are there any recommendation for improving the resolution of fluoride in sample containing high organics?
Great question.
Yeah, I said any recommendation for improving the resolution of fluoride in sample containing high organics?
That's an excellent question. I don't think I can answer that without thinking about this and researching it a little bit. I'm very happy to look into this matter, though, and get back to that particular customer, if you can take note of who this is.
Claro. Okay. Gracias, Pamela. Vamos a revisar la respuesta y le vamos a pasar la información a los distribuidores. Si usted es cliente de alguno de nuestros distribuidores, por favor, comuníquese con la persona de contacto y le pasaremos la información. Muchas gracias. Is there any other question? ¿Alguna otra pregunta? The señor Jorge Valentino, is the suppressor the maximum pressure so as not damage the exchange resin? So I think he's asking for the maximum pressure of the suppressor.
Yes, we approached this subject recently because we were hyphenating our prominence IC with mass spectrometer. And in doing so, we were noting a valve that was in position in the configuration between the flow cell of our conductivity detector and the mass spectrometer to be able to switch the valve in and out. So we were concerned that when the valve turned, that we weren't introducing too much back pressure. And in looking into the matter and then consulting the engineers at Shimadzu in Japan, we were able to determine that the suppressor is able to easily withstand 5,000 PSI of back pressure, which far exceeds my need.
Right.
So in other words, that can be important when you're wanting to add additional detectors after the conductivity detector, perhaps.
Right.
And
non-destructible detector.
So it was quite forgiving that way.
Okay. And the pump pressure, they allow all that pressure in the pump. Okay. So I missed one question here from la señorita Rocío Girón. She's asking, it is necessary that ion species are soluble in water to do analysis?
That's an actually a complicated question, because the anion species of interest that I would recommend the most with our prominence IC is because our suppressor demands that the eluent be highly aqueous and not have much organic content for the health of the suppressor. So I want the analytes to be water soluble. My guess is that the nature of the question is because this customer's samples are highly organic or in some non-aqueous matrix of some type. As long as the mobile phase, that is the eluent, is also highly aqueous, sodium carbonate, bicarbonate based, and you have solubility of your sample in that, then I would say we have a lot of freedom to inject lots of different types of samples. So if that customer has a sample type that is non-aqueous, the fact that you're injecting only 50 or 100 microliters, I think you'd be fine as long as that sample is completely soluble in a water matrix. If that's true, then you'd be very successful.
Should be able to separate everything.
Yes. Yeah. Okay. So we just want to make sure that the eluent itself doesn't have any organic content.
Yeah, the eluent. Okay.
But the sample matrix itself can have an appreciable amount of organic, and you'll be fine.
Okay.
I hope I answered that question.
Perfect. Let me see if there's another question here. I think I got everything. Any other question? ¿Alguna otra pregunta que quieran hacerle al señor Craig? Rocío Girón dice, thank you, gracias. ¿Alguna otra pregunta? Bueno, entonces no me queda nada más que decir gracias por su participación. Thank you very much for your participation. Thank you, Craig, for this excellent presentation. I hope everybody here have good information. Again, if you have any questions, this presentation will be available through our distributor. I will send this presentation in PDF or to all of our distributor. And also the video recording we did today for your future reference. If you have any questions, don't hesitate to, if you're a customer and you have any questions, don't hesitate to contact your local distributor and they will be able to communicate with us and get anything answered if needed, okay? Once again, I want to thank you everybody for your participation today and we hope you enjoy the rest of the day. Thank you very much. Thank you, Craig.
Thank you.
So on that.